And now welcome to the stage, Kevin.
Good afternoon. Today I'm going to introduce to you what we do at Deepmotion to use AI to create intelligent character motions. My name is Kevin He. So I'm the founder and CEO of Deepmotion. Prior to Deepmotion, I was in technical role at Roblox, Disney, Blizzard, some game companies. So we have a team who are passionate about creating intelligent character animation, but we're trying to solve a problem, how to use physics simulation to enhance the character movement. So first I want to talk about what's the difference between prescribed motion and simulated motion. We all know that classic animation relies on keyframe animation to create prescribed motion. So that's based on keyframe or based on motion capture, but every time you play, it's the same. It's highly crafted, and it's not very reactive. So in the domain of simulated motion, we use physics simulation to create the motion on the spot. So you have a more unique and flexible experience, and it's highly interactive. Then how did we achieve simulated motion at Deepmotion? So first, we create a physical model of human being. This is much simplified ones based on robotic model. Every bone in the virtual human will be modeled as one rigid body. Then you connect the rigid body with virtual joints. And then you apply virtual force at the joints to power the digital human around. So after building such a physical model, we apply physics to it. Then you get something we call Ragdoll in the game domain. So not very interesting yet. Then the second step, we basically apply more active control at every joint of the virtual robot. Basically actuate virtual muscle to pull the joints and drive the skeleton around. Then we have something called active ragdoll. In order to let this ragdoll standing there keep balance, we learn from robotics community to apply balancing theory. So the base theory is that if you project the center of mass of your body to the ground supporting plane, and if that projection is outside the supporting polygon, your character will be pulled forward or backward. You will lose balance. Then all we need to do is to actuate force as indicated by the green arrow. And those green arrow in the balancing theory, we can have a virtual character standing there and performing a suite of in-place motions, like squatting, like shaking the waist, kicking, etc. So this is the very beginning of our virtual character that's based on physics simulation. We then can apply this technology to a few interesting applications. So the first application we tried is to use this physics simulated character to represent the full body avatar inside the VR. As we all know, in the VR space, you typically have 3-point tracker. They are attached to your head and 2 hands. But from the 3-point position, how to recreate the full body movement, that's a very challenging problem. The traditional IK approach is very hard to tune, and it's hard to create lower body motion, etc. So we rely on this physical model to recreate a digital representation of the full body avatar that can hopefully capture more details of the virtual beings. So this is the first application where we apply a biomechanical model to do a full body avatar tracking. And this is another example of that full body tracking solution. Not only you can simulate one, you can also have two guys from remote in virtual space. They can hug and handshake with each other and generate some reaction between the virtual fight or virtual dance. And the next application, obviously we can apply this to NPC in AR space. So these 2 examples are captured from iPhone. So the left-hand side, we have 2 physics simulated schoolboys that bump into each other, and they have some kind of interaction. The right-hand side is a dog popped up in AR. We basically play some virtual toy with the dog. We use our phone to drag the dog around. The dog trying to apply the human balancing theory I showed, basically standing on the feet, not being dragged down. and then you have some interesting interaction between the virtual dog and the virtual toy. So that's the first phase of our experiment, to use physics to create the virtual motion. The second phase is to advance that state of art to use machine learning to further enhance the diversity of the movement. As we know, we can apply general reinforcement learning to learn physics-based motion from real human movement. The basic setup is that we take a few motion capture as the reference on the left-hand side, then we run a reinforcement learning framework to simulate that motion, and based on the success and failure of the simulation, we'll reward or penalize the model. Eventually, we'll train a model that can drive the character with simulation. So this process essentially automates the manual process in our first phase to create a balanced robot by hand. So now we run machine learning to train the model. So this is an example of the reference motion. It's just a 1 second mocap. This is after like 100 iterations of the training. Then you get a model that kind of works, but very unstable. And then if you keep running the machine learning for 1,000 iterations, you will train a muscle control model that's much more stable. It can not only mimic the input motion, but also offer some interaction when you drag the character around. So the dragging part is simulating in real time. And then the next step, we're trying to increase diversity of the virtual behaviors of this robot. And so in this example, we increase the number of reference motion from 1 to 3. So you have a running, turning, and get up. And then we stitch them together with a state machine. Then we train a more complicated control model to embody that 3 reference motion. Then you will have a simulated being that can do running, sharp turn, and climb up from ground after he's pushed off. So all this can endure disturbance from user or from script. And then if we increase the size of motion brain, you have more and more diverse behavior. And you can simulate eventually a crowd of people walking in the shopping mall, climbing up ladders, sit on the couch, etc. This is another example of use the same technology to simulate basketball play, dribbling. We can expand the same technology to animals, and using a few seconds of dog animation, you can create a virtual dog. And eventually, we want to put this on the cloud, offer developer a tool so that you can create digital motion from your own reference. So that concludes my introduction of physics-based motion for virtual being. Thank you.